There are some linear differential equations which do not fit the category of a standard linear differential equation. That is, they are first order differential equations, but then they are not linear, because either the derivative is raised to some power other than 1, or the dependent variable is raised to some power, so that it no longer is linear. So that the standard model of solving this linear differential equation does not work. At least it does not give us an equation which serves as the solution of the differential equation. The solution just doesn't work as a solution. One of these famous non-linear differential equations is the Bernoulli differential equation. Now, before we get into the Bernoulli differential equation, what we mean is that these are special cases of linear differential equations which, by a certain mathematical operation or substitution or some other operation, reduce to a linear differential equation of first order that we are familiar with, and after this operation is performed, the equation reduces to a form in which the algorithm that we discussed earlier works, and the solution that is obtained also works as a solution. So the first of these is a differential equation that was published by Jacob Bernoulli back in the year 1695. But Bernoulli only discussed this strange linear differential equation. He could not find any method to solve this linear differential equation. The actual solution of Bernoulli's differential equation was actually published by Leibniz in the year 1696. After Bernoulli first discussed this problem in one of his letters. So let us look at Jacob Bernoulli's differential equation, which can actually be reduced to linear differential equation. Bernoulli's differential equation. The differential equation of the type dy by dx plus py is equal to qy to the power of n is the Bernoulli's differential equation. Notice here, the q is multiplied by the term y to the power of n, where y is the dependent variable. It is the dependent variable such that dy by dx is the differential coefficient of this. So this is what sets it apart from the linear differential equation of first order that we have discussed. So here y is raised to the power of n, where of course if you put n is equal to 0, it will reduce to the form of the differential equation that you are familiar with. If you put n is equal to 1, again it will be a linear differential equation which we can solve. But then it no longer remains linear if y becomes, say, any value greater than 1, say 1.5 or 2. The standard forms in many of the actual practical applications, like for example, there is a certain differential equation, a special type of differential equation of this type called the logistical differential equation. So in there, the value of n is 2. So therefore, how do we actually solve this? What was the solution that Leibniz proposed? Let's look at that. So here, p and q are constants or functions of x alone, just like the standard linear differential equation. N is a constant other than 0 or 1. Now this Bernoulli's differential equation can be reduced to the linear form by doing what? By dividing both sides by the troublesome factor, y to the power of n. So therefore, what does it become? It becomes 1 upon y to the power of n dy by dx plus 1 upon y to the power of n times py is equal to qy to the power of n by y to the power of n. And so we get y to the power of minus n dy by dx plus y to the power of 1 minus n times p is equal to q. Leibniz then suggests that we substitute y to the power of 1 minus n in terms of another variable v. So this change of variable is what reduces it to a standard linear differential equation of the first order. So what do we do here? We write dv by dy is equal to 1 minus n dy upon dy y to the power of minus n. And then you can use the chain rule to write it in terms of x, and then it reduces to the standard differential equation that we know of, which you can solve. We can look at practical examples of the application of this and the demonstration that this method works in the following example.